Okay. The first thing I want to talk about is for next week, Wednesday, Inauguration Day, with everything going on. I've decided that it's either going to be stressful or a huge relief. And either way, no one's really going to be wanting concentrating on school. So I am not going to have any new material or lectures on Wednesday next week. I will be available for office hours. So if you have any questions and want to work through anything that we've covered up till that point, feel free to come on in. I will be available. Okay. And I'll post an announcement to reinforce that on Canvas. Any questions about that? The homework, I'm waiting to hear back from SmartWorks. Rico, come on, dude. Waiting to hear back from SmartWorks. I allowed for late submissions with a penalty, but for whatever reason, for some of you, it was locking up. So if you've noticed that I changed the due date, it was because it wasn't allowing people to continue working on it, even though you should have been able to. So I'm waiting to hear back from them how to fix that so we can keep it going. If anything, I mean, worst case scenario, I just extend it beyond the due date and there's no penalty. But what you want to do is get that done on time, as that'll keep you in the swing of things for the schedule for the class, so you don't find yourself falling behind. But I'm not really all that concerned with things being so timely this quarter and next and the ones before. Any questions on that? Okay, then this Friday will be our first quiz. So again, when you come in on Friday, what I'll do is just randomly assign you to breakout rooms. And then you can go in there and start working on the quizzes together. And again, after you've submitted once and given it like your first real good effort, if you get stuck and can't figure something out, then by all means, just call me into the room and I will walk you through how to do the problems. The quizzes are not meant to be a test. They're meant to be a learning experience for you and give you a chance to kind of practice for exam taking. So you'll know the best strategy you can possibly have for tackling those. Any questions on that? Okay, so before I start new material, any questions on the lectures that I posted for Monday and Tuesday? All right. Let me start sharing my screen. So today, come on, there we go. Today is building off of what we've been doing. Oh, sorry, give me a second to find my window I want to share. That's not the one I want. I'm sorry, give me a second, technical, there we go. Okay, Chihuahua, relax. Can you see the slide that says lecture 2.4? Okay. Today, what we're going to do is build off of the reaction quotient, which was the last bit of lecture for Tuesday. And we're going to incorporate that concept into a new concept called the Chatelier's principle. And all that means is, sorry, if I change something in the reaction, how does the reaction react in response to that change? And what the Chatelier said is that if something is at equilibrium and then I make a change to it, the system is going to try to adapt to where I get back to equilibrium, which is kind of just a straightforward way, because in other words, if I add more reactant, I'm going to get more product, right? So we can look at things and see how a reaction will progress, just kind of keeping in thinking with Le Chatelier's principle. And let's do some examples on it and how things can change and what we're going to predict about the change based on the change, what we're going to predict on equilibrium based on the change that we do with our reactions. Okay. So if a system is at equilibrium, Sorry, let me get my screen so I can actually see what I'm doing. Okay, it's not going to work. All right. If a system is at equilibrium and I change concentration, partial pressure, temperature, or volume, the system is going to react to reestablish that equilibrium. That's all I was saying in the previous slide. So let's see how that plays out. This is like one of the most abundant reactions that are done.
Going back just really quick so we can take a picture of the definition, if that's
okay.
okay.
Yeah, and just so you know, they are posted on Canvas.
Okay, thank you so much.
You're welcome. Yeah, so you can pull them up on Canvas if I'm going too fast.
Okay, sorry about that.
Oh, no, by all means, speak up. All right, so the production of ammonia, that's a huge industrial process. That's for everything we use for fertilizer, right? So this particular reaction then is one of interest for how do we speed it up, or how do we produce more ammonia in doing the reaction? This table that we're kind of used to looking at, except for it's just kind of starting off with the flat line. So what you're not seeing is the kinetic part in the beginning, but our concentrations aren't changing with time. So that tells us that the system is in equilibrium. So now let's think what happens. If I have my H2, actually, let me back up a second. If I look at the reaction, hopefully it makes sense that I have more H2 than I do ammonia and nitrogen. So before I go into equilibrium, why would I expect that to be true? What can I look at when this reaction to predict how much I would have of each? Hannah.
It's a good thing my dog's not hearing that.
I know, I'm sorry. The wind is blowing, so today's probably not going to be real smooth with dog noises.
Does it have to do with the coefficients?
Yeah. So we have this stoichiometric ratio of everything, right? And the one with the highest coefficient is hydrogen. So I would predict that I'm going to have the most amount of hydrogen at equilibrium, and then the next one down ammonia, and then the bottom one nitrogen. So now let's think, what is going to happen if I add more hydrogen? Think about it for a second. Do you think I'm going to decrease the amount of ammonia, increase the amount of ammonia produced? Nothing's going to happen, or you can't tell. Let me see. I want to launch my poll. There we go. Some of you thinking about it still? Or do you need more coffee? Good. Somebody who chose B, why B? Why not C? David.
I was about to because I chose B.
You chose B?
Yeah.
Okay, so why not C?
Because there's going to be, I thought there was just going to be a little bit more NH3 because more hydrogen was being added to the nitrogen, and the nitrogen needs the fewest amount of moles.
Good. Now, what does my reaction quotient look like? So I have Q, remember that's my reaction quotient. Somebody different, give me an expression. What's my reaction quotient expression? Say that twice fast. Lucy.
I'm not entirely sure.
Okay, let me ask you this. What's K? We'll go KC.
Oh, NH3 to the power of 2 over H2 to the power of 3, and then times N2.
Perfect. So Alina, what's the reaction quotient expression?
You know, I'm going to be perfectly honest. I didn't get to that video, so I'm not sure. I'm sorry.
That's okay. Did anybody get a chance to watch it?
Would it be the same because doesn't Q equal K?
So careful, you're right. The expression is the same. What does it mean if Q equals K? And with respect to equilibrium, I should say.
Does it mean that the system is at equilibrium?
Perfect. Yep. So I'm going to write this down for those of you that may not have gotten a chance to write or watch those videos. So if Q equals K, then we're at equilibrium. What do you think it means if Q is less than K? Are we at equilibrium or have we not gotten there yet?
Not gotten there yet.
Good, good. So we are approaching equilibrium. And that means that we're still making product. So my equilibrium is progressing this way. If Q is greater than K, which direction is my equilibrium going? Which direction do I have to go to get to equilibrium, I should say? Davey.
To the left.
Good. So now let's look at this same question in terms of our equilibrium constants. So if I look at Q, I come over here and I look at Q, if I increase hydrogen, is Q going to be smaller or larger than K? Grace.
Smaller?
Good. So if it's smaller than K, then my equilibrium is going to progress towards the right, which means I'm going to make more product. Does that make sense to everybody? To me, this is probably the easier way to really get my brain in the equilibrium mode. I'm sorry, the Le Chatelier mode, because sometimes it feels counterintuitive. So thinking of it in terms of what's happening with my equilibrium constant, or rather my equilibrium quotient, helps me kind of keep track of how something will go. And we can come here and we'll look. We see if we added the hydrogen, you can see in this region, my concentrations are the same. So I'm in equilibrium here. And my concentrations are the same here. So I'm in equilibrium. And then this would be my kinetic region. So we can see I have this steep spike. That's just me adding in more hydrogen. And then my nitrogen down here is going to decrease because I've added more hydrogen to react with it until we stabilize. So obviously, if this is decreasing and this is decreasing after I've added it, then I've increased the amount of product. Questions on that? Are we good? Okay. So now, Rico, go away. I'm going to change the counts. Rico, dude, go. We're good. Combustion of ammonia. I have, in this reaction, I have ammonia reacting with oxygen, combusting to produce nitrogen and water. So let's think about how the amount of ammonia is changed by altering the reaction in a few different ways. So I am going to remove some oxygen. Relaunch the poll. What's going to happen to my ammonia? Am I going to decrease the quantity? I'm sorry, more ammonia. Oh, that's why my arrows, I'm like, that's confusing. So am I going to force the reaction to go to the left, to the right? So more or less ammonia. Nothing happens or you can't tell. Okay, we have kind of a mix going on here. Vast majority of you are choosing A. So why A? Somebody explain. Amelia.
I didn't have very like scientific way of thinking of it, but just by looking at the problem, I was thinking if removing the oxygen, then it wouldn't be there anymore, and there would just be more NH3.
Okay, so what does Q look like? What's my equation for Q? Kelly.
Would it be N2 squared times H2O to the 6 over NH3 to the 4 times O squared to the 3rd?
Perfect. So there we go. So if I decrease the concentration of oxygen, is Q going to be larger or smaller than K? Josh.
Larger.
Good, good. Because I'm making the denominator smaller. So that means overall Q would be larger than K. So to progress to equilibrium, my reaction is going to go this way. It's going to favor my reactants, not my products. Does that make sense to everyone? Questions on that? Good. What if I add nitrogen? Let me resubmit my poll. Now I'm going to add nitrogen in. What's going to happen to my reaction?
Are we adding nitrogen after we've already reduced the O2?
So this is just going to be a separate thing. So think of it as we're at equilibrium. I haven't changed O2. I'm just adding in nitrogen.
Okay.
And if you need a hint, look at the equation for Q. Adding a nitrogen in, is that going to make Q larger or smaller than K? Ooh, we're pretty evenly split between A and B. So somebody who chose B. Explain to me your reasoning. Faith, what do you think? Is it A or B?
I'm not sure, but I think I'm leaning towards that there will be no change.
No change? So
Nothing
what does
happens.
Q tell me?
If they have, if it's equal and the reactants are at the equilibrium,
Okay, so if Q equals K, we're at equilibrium. If Q is less than K, which direction is the reaction going to go to get to equilibrium?
towards the products.
Good. And if Q is greater than K, what's going to happen?
If Q is greater, then it goes towards the reactants.
Good. So in this case, if I'm adding in nitrogen, is it going to be equal to K, less than K, or greater than K?
Would it then be greater than K
Good.
or less?
Greater than. Yep, because it lives here.
Sorry, can you repeat the question?
If by adding nitrogen, is Q going to be larger or less than K?
Larger.
Good, good. So if Q is larger than K, then that means I am favoring my reactants. So I'm going to produce more ammonia. So more NH3. Action's going to go this way. Q is again greater than K. Another way to think about that is in terms of kinetics. Remember, we define a rate of reaction in terms of our reactants with that little k and then the concentration. So if I increase the concentration of something, then that means I've increased the rate of that reaction going in that particular direction. So in this case, I would have my N2, my nitrogen and my water. So increasing either of those is going to increase the rate of my reaction because I've increased the concentration. Or going back to it conceptually, I now have more of that thing. So more of those molecules in my beaker or my container that are going to collide. The more collisions I get between two reactants, the more product I'm going to get. So there's kind of the few different ways to think about that. What if I remove water? Let me relaunch my poll. If I remove water, what's going to happen? Am I going to have more ammonia, less ammonia? Nothing happens. You can't tell. I think there's 5 or 6 of you that need more coffee. Good, good. So somebody who chose B, why B?
I chose B because if the concentration of H2O goes down, then the numerator would be smaller, so then Q would be smaller than K, and it would proceed forward, so there would be less ammonia.
Perfect. Awesome. So Q will be less than K. Oops, K. So my reaction is going to go that away. Are we all good with that? So less ammonia. And I know that this is a tricky concept for people to really get comfortable with. So if you are sitting there still trying to come to terms with this, Don't worry, there's a reason why we're going to do a lot of examples today and again on Monday. So be kind to yourself. All right, so let's take a look at endothermic versus exothermic. Hopefully you guys got to Hess's law. If you didn't, that's what the delta H stands for, and not Hess's law, but enthalpy. And enthalpy is typically tackled using Hess's law. In this particular reaction, you're given a delta H, or an enthalpy value of negative 206 kilojoules per mole. So this is for carbon monoxide reacting with hydrogen to produce methane and water. Is this an endothermic or an exothermic reaction? McKenna.
Honestly, I'm not super sure.
That's okay. That's a fair answer. Owen.
This is an exothermic reaction.
Good, good. So it's an exothermic. How do I tell?
The enthalpy is negative, and therefore it's releasing energy.
Perfect, perfect explanation. So that means that if you see the negative sign, the system is losing energy. A positive sign means I have to put energy in. So now let me ask you this. Which direction is it exothermic? To the right or to the left? Nikolai.
I would be inclined to say to the right.
Good.
I don't completely remember why.
Okay.
I don't know if I could explain that.
Okay, let me ask you this. Which direction is the equation written? Which ones are my products and which ones are my reactants? The left or which side is my products? The left or the right side?
Oh, the right side is the products.
Good, good. So my reactants are over here. And here's my products. So what that means is that if I put these things in my beaker, I'm going to get this exothermic reaction. So it's to the right. What happens if I flip that reaction? Do I change the sign of enthalpy or is it the same?
You should have to flip the sign of enthalpy because it's going to be the reverse reaction. So you're going to need that. Yeah.
Perfect. Spot on. Oops, forgot I made that a poll. So then which direction is endothermic?
The products to reaction. The products to reactants.
Good. So for this one, which direction is exothermic would be that way. What direction is endothermic is this one. Another way to think about that is if I flip that reaction, going back to the question that I just asked, that means I'd have to change the sign on my enthalpy. That means if I put methane and water together and I wanted to produce carbon monoxide and hydrogen, I would have to add that amount of energy into the system to get those products, those now what I would call products. Does that much make sense to everybody? Are we comfortable with that? Okay. Now let's add a little layer in there. Something is going on here. If I look at my Kc values, at room temperature, I have this ginormous K. So my products are very much favored here. But as I increase the temperature, my Kc is going down substantially. So an increase of 4 has decreased my K by a factor of like 27. That's huge, a magnitude of 27. I'm going to put you into breakout rooms. I want you to discuss why you think that might be. And the hint I'm going to give you for your discussion is to consider it in terms of enthalpy. What do you think is going on here? So I'm going to stop sharing. Okay, so what did we come up with? Sean.
Our group is kind of talking about something about how the KC is kind of the concentration, and potentially as the temperature goes up, we were thinking maybe the rate would potentially go up or something like that.
So if the rate goes up though, what direction would the rate be going up?
Oh, well, the reactants would be consumed quicker, maybe.
Okay.
The products.
Okay. Katie, what do you think?
Our group was kind of talking about the Gibbs free energy equation.
Okay. What'd you come up with that?
And just the idea that at lower temperatures, for an exothermic reaction, it would be spontaneous at lower temperatures, but higher temperatures, if the entropy is negative, then it would no longer be spontaneous.
Perfect. That is a great way of thinking about that. And I'll do a video for all of you that are now saying, wait, what? I'll do a quick little short video reminding you or exposing you to Gibbs free energy for the first time. And it'll just be an optional one just in case. So let's talk about this. Another way to look at this is activation energy. So let's see, this would be like the energy of the system, temperature of the system at some time. And I add in this teeny tiny amount of energy. So for something that's exothermic, you'd be looking at the differences in these temperatures. So the temperature in the end, the amount of energy I'm losing in the end is what the system is giving off. So this just needs like this tiny amount of activation energy. Going in this direction, I have all of this activation energy that I need to throw in there in order to get the reaction to go. So if I increase the temperature, I am increasing the amount of collisions that are happening within the system, and more importantly, I'm adding energy in. So if something is going to be spontaneous at lower temperatures, which was in terms of Gibbs free energy, then that means that as I add temperature in, I'm increasing the amount of collisions, then these guys are going to hit each other more frequently and with more energy. And so I'm going to get this kind of thing going to where I'm going to end up forcing my reaction to go to the left. And that means I'm simultaneously decreasing my K values as I increase that temperature. Because remember, K says how much product or reactant, how much product I'll get. So a really large K, lots of product. Small K, not so much. Is everybody good with that? Okay. Here's just kind of like a summary of all of that. So if something is endothermic, one way to think about it to kind of get the brain more comfortable with this idea of the change in temperature. If something is endothermic, you can think of that as heat being needed on the reactant side of an equation. So if I add temperature in or I increase the amount of heat, I am now going to force the thing to go towards my products. So increase the temperature on something that's endothermic, I'm going to produce more products. My K is going to go up with my T, my temperature as it goes up. The previous example was the opposite, was something that is exothermic. So if I increase the temperature on the reaction, then my K is going to decrease. And you can think of that in terms of heat now being on the opposite side of the equation. So it was just like all the other reactions we were doing. If I add heat in, I'm increasing one of the products, which is going to drive the reaction to the left to get to equilibrium. Does that make sense to everybody? Okay. So we want to, oops, there we go. We want to see what temperature we need to maximize the octane production. The octane, by the way, is the C8H18. So I'm going to react carbon monoxide and hydrogen to produce my octane and my water. And you're given that delta H. Let me relaunch my poll. What temperature do you think you would want to increase, or what's going to happen, more or less octane if the temperature increases? Okay, we're pretty evenly split here between A and B. So let me remind you of just kind of the way to look at this then is that I have, here we go, 8. Actually, instead of writing it there, this would be plus heat, right? So my delta H is negative. This means this is exothermic. So I can look at this in terms of my reaction quotient and be like, okay, so here is my methane, I'm sorry, my octane, H18, and my water. Does somebody have a question? Something just flashed on the screen. Okay. Carbon monoxide to the 8th and to the 17th. That's huge. All right, so if I'm considering heat as one of the products, I would put it up here. And we're never going to do this mathematically because this is just a figurative to help you kind of keep straight what's going to happen. If heat is on the top and I increase the amount, is Q larger or smaller than K?
It'd be larger.
Yeah, it's on the top. So Q would be larger than K. So what direction is the reaction going to go to reach equilibrium? To the left or to the right?
Be going to the left, right?
Perfect. Yep. So my reaction would go this way, which means that I'm not going to produce as much of my octane. So there is nothing wrong as we're working through this to really chew on and use Q, and then to force yourself to think it through conceptually. So think in terms of what's going on inside your beaker, and am I increasing interactions? What's going on with my activation energy? Am I adding energy in enough to make things go one direction or the other? But all else fails, while you get comfortable with that, just go in terms of Q and compare the two. Any questions on that? Okay. How would you expect the time to reach equilibrium to change? So now think in terms of my rate of reaction. Is it going to increase or decrease with an increase in temperature? Oops, let me relaunch. You think it's going to speed up, slow down, stay the same? Can't tell. This is rate, not equilibrium. Holy moly. Okay, we're almost evenly split on that one. So somebody that said increase, why do you think increase? This is the time for it to reach equilibrium. Why would the time increase? Samantha.
Because Increase the temperature, you add energy in, so it'll speed up the reaction.
Ah, okay, now I see what's going on. So the question is it going to speed up, so increase the time it takes to reach to reach equilibrium? So if I'm speeding it up, I'm decreasing the time it takes. Are you good with that?
Oops, I read it wrong.
Yep. Nope, I can see how, yeah, that it gets confusing with all the increase and decreasing. So yeah, if I add heat in, I will in fact speed it up, but I'm just going to make less. So that's kind of like the give and take that people in industry have to work with, is producing more or producing it expeditiously, which is the better option for whatever circumstance they're working with. So we have 3 minutes left. What I'm going to have you do, I want you to chew on these questions. Think through lecture today. And again, I'm going to do it on Monday, and we're going to hit this Friday on the quiz to reinforce this, because I know it's a tricky concept. So, but do yourself a favor to reinforce it, both talk amongst yourselves and think these through. First, answer them without looking at your notes, then go back through and look at your notes and address the questions. And then I will do a video and post it for Monday, explaining everything, or answer your questions on Friday during the quiz. Is everybody clear on what I want? Cool. All right.